Okay, here's an example using motion in 2 dimensions. So the particle leaves the origin. So the origin mentioned here is important because, of course, this tells us the initial position. With an initial velocity, you can see here that initially the velocity is entirely in the x direction, so along this I vector, and a constant acceleration. So there's no t dependence here, and you can see we have components in both the x and y directions. Then the question asks us when it reaches its maximum x coordinate. This is important. We'll come back to that. What are its velocity and position? So the reason this is important is because it determines our strategy for the question. Ordinarily, for a question like this, where the velocity and acceleration are given to us in this component form, my preference would be to solve this problem with both the x and y components simultaneously, basically in vector form. But because the question asks us explicitly for the x coordinate here, at some point we're going to have to address the x part by itself. And so it's actually easier to solve this problem by treating the horizontal and vertical components separately. So let's see how we do that then. So for the horizontal and vertical components, what are we going to do? Okay, well, we're going to use our Suvat equations exactly as we learned how to do last week in 1 dimension. And the Suvat equations, as we learned them at school, probably something like this. So V equals U plus AT. But the way that we wrote this down in the notes was to note, well, sort of our final velocity is equal to our initial velocity, V naught, plus our acceleration times time. So it's the same equation, just different notation. Okay, and these are vector quantities. We also have this equation, S equals ut plus a half at squared. And the way that we're going to be using that equation, well, the position, it's either going to be x or y. Okay, I'm just going to write it down in terms of x now. The displacement here, this S, well, that's just the difference between my final and initial positions. And on the right-hand side, I'm going to have my initial velocity. So that's, say, again, our V naught times the time plus half our acceleration times the time squared. So these are the forms in which I'm going to be using these equations. And these are all vector quantities, so we should all have these little marks on them. But in this case, we're going to see that we're going to have the y component of this as well, because we're going to be treating horizontal and vertical separately. So for the horizontal motion, first of all, we have that our final velocity v in the x direction is equal to our initial velocity in the x direction plus the acceleration in the x direction times the time. And we're given in the question that the initial velocity in the x direction is 3, okay, because we're told that the velocity here is 3I, so that's entirely in the x direction, plus the acceleration in the x direction. Well, again, in the question, it tells us the acceleration is -1. So that's going to be -1 times the time. Okay, so this is just Vx is equal to 3 minus the time. Okay, what about the vertical component then? Well, we have the y part of this, so that's going to be the initial velocity in the y direction plus the acceleration in the y direction times time. And v naught y, well, initially it's moving entirely in the x direction, so there is no v naught y, so that's 0. Plus ayt, well, the y component of the acceleration is just -1/2 times t. Okay, so that's our velocity in the y direction. Okay, what about this equation then? So we'll have that x minus x naught. So x naught in the problem, well, we're told that it leaves from the origin. So x naught is just going to be 0. So x minus 0 is equal to the velocity, the initial velocity in the x direction, which is 3, times the time, plus 1/2. And then the acceleration in the x direction, again, is just -1 times t squared. So we'll have that x is given by 3t minus 1/2 t squared. That's our expression there. What about for the y direction? Well, again, we'll have position y minus our initial position, but our initial position, again, is the origin, so this y0 is 0, is equal to the initial velocity, which again, in the y direction is 0, times time, plus half our acceleration. So half the acceleration in the y direction is -1/2 times t squared. So we end up with y is equal to -1/4 t squared. So now we have these 4 expressions. We've determined the position, or the horizontal and vertical components of the position in terms of time, and we have the horizontal and vertical components of the velocity in terms of time. Now, the question asks us about this specific moment where we reach the maximum x coordinate. Now, when you're finding the maximum value of some function, you know that you find the derivative of that function with respect to the independent variable and set it equal to 0. So in our case, what we want is to find the moment when x is no longer changing, i.e. the moment where this dx by dt is equal to 0. This is just the definition of the velocity in the x direction, though. So if we can determine when the velocity in the x direction is 0, that tells us when this quantity x is maximal. And that's actually nice and easy because we have this expression here, vx equals 3 minus t. And so from that, we can determine, so if I number these equations, so I'll say 1, 2, 3, 4, we can say from equation 1, we have that 0, or sorry, vx equal to 0 equal to 3 minus t will tell us that t is just equal to 3 seconds. So the moment at which x is at its maximum is when t is equal to 3. So then what do we do that information? Well, we have to determine the velocity and the position. So we're just going to plug this value of t equals 3 into equations 1 and 2, first of all. So let's call this equation 5. And we're going to substitute equation 5 into 1 and 2. Well, we already know when we substitute t equals 3 into this expression, we're going to get that vx is equal to 0, because that's how we defined this time. It's the time when the velocity in the x direction is 0. So our velocity in the x direction is 0. Our velocity in the y direction, well, 0 minus a half times 3 is just minus 1.5. So Vy is minus 1.5 meters per second. Okay, so we can write down that velocity at that moment, t equals 2, is equal to minus 1.5 j meters per second, if we want to write that in vector form. Then to find the position at that moment in time, well, again, we just substitute in our value of t into equations 3 and 4. So let's substitute 5 into equations 3 and 4. And when we do that, we get x equal to, well, substituting in t equals 3 here, we get 3 times 3, which is 9, minus a half t squared, which is a half times 9. So we get 9 minus a half 9, which is just 4.5 meters in the x direction. And in the y direction, again, we'll substitute in t equals 3 here. We'll get a quarter times 9, so minus 9 over 4. Minus 9 over 4, which is just minus 2.25 meters. So again, these two together define our final position. So position operator r at time equals 2 is just equal to, in fact, I'm going to write it out down here because I'm not going to have enough space otherwise. R at t equals 2 is just given by 4.5 I minus 2.25 j meters, and that's the position. And that's our example.